Researchers in artificial intelligence believe that the path to AGI or artificial general intelligence is by leveraging the agentic AI workflow. But what exactly is an agentic AI workflow, and how can we use it in our daily tasks and business decision making? To find out, we will go through several important concepts in AI developments using examples from prominent research studies that I will share with you today. Most probably you've been interacting with AI as a zero-shot use of large language models and chatbots. For example, asking an LLM or chatbot to generate a text, story, code, or image for you, and sometimes getting disappointing results. But there's a much better way of interacting with an LLM or any AI tool, and that's to make an agentic workflow. To give an initial simplified understanding of it, an agentic system asks the same model to refine its outputs in an iterative process using a series of feedback to get to the final answer or results on a task. This is pretty much how humans complete a task. We just don't sit there and complete a task from start to finish. Instead, we make a series of revisions on multiple iterations of our works by redrafting, proofreading, fixing the errors, asking our colleagues for critical comments, and so on to complete a project. This is illustrated by this research study, SelfRefine, Iterative Refinement with Self-Feedback by Medon et al. In 2023. As they put it, the main idea is to generate an initial output using an LLM, then the same LLM provides feedback for its output and uses it to refine itself iteratively. SelfRefine does not require any supervised training data, additional training, or reinforcement learning, and instead uses a single LLM as the generator, refiner, and feedback provider. They tested this new method across 7 different tasks, including text and code generation, and found that the self-refined versions outperformed their base generative models such as GPT-4. They also noticed that the outputs keep improving with more iterations. This ability of an AI system or language model to correct and refine itself is also referred to as reflection. You can see an instance of it in this new framework, Reflexion Language Agents with Verbal Reinforcement Learning by Shin et al. In 2023. The authors showed that using linguistic feedback and asking the model to self-refine itself is more effective than the traditional reinforcement learning method, for example, by updating weights. As you see, the new reflection method outperformed previous refinement methods on reasoning and decision-making as well as code generation. You might have already experimented with this before, for example, by asking ChatGPT or any local LLM to give you an alternative or better output or to correct a faulty code. But did you know that now algorithms can do this for you too? Let's take a look at one of these algorithms. The reflection method of agentic AI uses verbal reinforcement to help agents learn from prior failings. Reflection converts binary or scalar feedback from the environment into verbal feedback in the form of a textual summary, which is then added as additional context for the LLM agent in the next episode. An evaluation signal which helps the system to find the cause of an error or problem further amplifies the feedback in the previous step. These 2 feedback blocks remain in the long-term memory and then passed to the actor, which is built on a large language model. This iterative process continues until the desired output is received from the agent. I highly recommend you read this paper to see how this interesting evaluator component works. But that's not all to agentic AI systems. A main component in the agentic AI workflow is the ability of these generative models and large language models to use tools just like humans to perform a task. If that's new to you, keep watching. This paper even proposes agentic systems that can access a variety of tools via API calls. The authors have also made a tool called Gorilla, which is based on Llama and can effectively write API calls with accurate arguments. Look at this example where Gorilla outperforms both GPT-4 and Claude in an API call. They successfully tested Gorilla on a document retrieval task and even built a comprehensive API dataset that all LLMs can use as part of completing a user task. Is that not so cool? The third important concept in an agentic AI workflow that I wanted to share with you is planning. In the words of Andrew Ng, it is giving the LLM the chance to work more slowly and plan the completion of a task in steps, for example, by explaining the reasoning behind each result in clear steps. This concept is explained in this paper as chain of thought prompting, or providing a model with a series of intermediate reasoning steps that they claim can help LLMs tackle complex reasoning tasks. They show how prompt engineering with a chain of thought outperforms standard prompting across various language models and test datasets. Feel free to pause the video and read these examples of the chain of thought that are implemented on a famous reasoning test, GSM-8K. I've already made a video about this test dataset. I'll put a link to it in the description box as well. This concept of AI as a controller of other AI models has already been implemented in HuggingGPT as described in this paper. What the authors have done is essentially use ChatGPT as a controller to receive the task prompt from a user and then divide it into subtasks. The controller then uses any relevant model available in the Hugging Face repositories to perform the subtask and retain the results, and even combine the results of multiple AI models for very complex tasks that involve multiple modalities such as text, speech, and vision. An example of it is to generate an image of a girl reading a book with her pose being the same as another image provided to the agent, and finally to describe the new image in your voice. This really fascinating framework follows 4 stages of task planning, task selection, task execution, and response generation that you can also use to complete your projects. I will leave the full reference of this work in the description box so you can also check out these examples such as visual question answering and object detection. As if these advancements aren't cool enough, we have now a very exciting framework for multi-agent collaboration as well. Just as multiple AI models or LLMs can collaborate on one task to make an agentic system, we can get multiple agentic systems to collaborate with each other too. Think Crew AI or AutoGen. What's even more interesting about systems such as AutoGen is the collaboration between humans and multiple agentic systems. This is so important because in some cases, human input and judgment become necessary to direct the course of action by LLMs and their agentic designs. This step is usually done by customizable and conversable agents. The cherry on top is that many of these systems and algorithms are already open source, which means you can use them right off the bat to build your own applications. The authors of AutoGen, for example, showcased 6 applications and use cases such as math problem solving, retrieval-augmented chat, ALF chat, for example, based on the idea of ALF world in this application as an AI detector and navigator, multi-agent coding, dynamic group chat, and conversational chess. But these are not just potential use cases. The ChatDev application has already been built on the same idea that is fully described in this paper, Communicative Agents for Software Development. ChatDev is a virtual company that employs multiple agents with different roles in the process of software development, such as designing, coding, testing, and documenting agents. Each of these agents could use multiple LLMs or generative models that mimic what human engineers do and converse in a real-world company. For example, self-reflection, instructions and testing, and so on. The authors documented how this multi-agent workflow significantly reduces the costs of software development, even when using API calls. But they emphasize that because these systems are in their initial development stages, there are some biases and risks involved in the process, depending on the choice of LLMs and their training data. Can we build an internet-like system for autonomous agents? This was a question in the minds of these researchers at Beijing University who have built the Internet of Agents or IOA system for large language models, inspired by how the internet works. More specifically, decentralized collaborative projects such as Wikipedia and Linux. Just like how the internet connects people, a system like IOA can connect different AI agents across different environments, where agents can form teams and sub-teams on their own and adapt to complex tasks. Originally discussed in this paper, Internet of Agents, Weaving a Web of Heterogeneous Agents for Collaborative Intelligence, the IOA system proposes a scalable platform for LLM-based multi-agent collaboration. The idea is to use autonomous agents that are capable of achieving near-human performance on a wide range of tasks and get them to break down complex tasks into executable steps by using various tools and learning from feedback and experience. As with other AI agents, this agentic framework also revolves around multitasking, using the asynchronous task execution capabilities in this system. As this conceptual layered architecture shows, the IOA system can bring together agents with different skills and backgrounds in what they call heterogeneous agent integration. This is a really interesting feature as it combines custom agents with third-party agents. The IOA framework consists of two main components, the server and the client. The server acts as a central hub, managing agent registration, discovery, and message routing. The most interesting part of it is that it enables agents with varying capabilities to find each other and initiate communication. The client, on the other hand, serves as a wrapper for individual agents, providing them with the necessary communication functionalities. These two server and client components sit on a layered architecture with 3 layers of interaction, data, and foundation. On the server side, the interaction layer facilitates team formation and agent communication. The agent query block enables agents to search for other agents based on specific characteristics. The group setup block facilitates the creation and management of group chats, and the message routing block ensures efficient and accurate routing of messages between agents and group chats. The data layer manages information related to agents, group chats, and tasks. In this layer, the agent registry block maintains a comprehensive database of registered agents, including their capabilities and current status. The session management block manages active connections and ensures continuous communication between the server and connected clients. The final layer, or the foundation layer, manages the entire system by providing essential infrastructure for agent integration, data management, and network communication. In this layer, the data block is responsible for data persistence and retrieval, the network block manages network communications, and the security block implements authentication, authorization, and other security protocols. The client side also has a super interesting and thoughtful design. The interaction layer manages the agent's interactions within the system. The team formation block implements the logic for identifying suitable collaborators and forming teams for the task at hand, similar to coalition formation in conventional multi-agent research. Complementing this, the communication block manages the agent's participation in group chats and handles message processing. The data layer functions as the agent's memory and maintains local data relevant to the agent's operations. It includes the agent contact block for storing information about other agents the current agent has interacted with, the group info block for maintaining details about ongoing group chats and collaborations, and the task management block for tracking the status and progress of tasks assigned to the agent. And finally, the father figure foundation layer provides the basic functionalities for the client's operations. The agent integration block defines the protocols and interfaces for integrating third-party agents into IOA ecosystem. Alongside this, the data block handles local data storage and retrieval, while the network block manages network communications with the server. I'm sure you agree that this is a very thoughtful architecture, considering all practical aspects of running the system and bringing together in-house and third-party language models. The authors have also put a lot of thought and consideration into the flow of conversation among agents, as you can see in this image. You can easily see how this is implemented through this 5-stage design. In the discussion state, the agents engage in general dialogue, exchanging ideas and clarifying task requirements. In the synchronous and asynchronous task assignment, tasks are assigned to specific agents with and without pause. The pause and trigger state waits for the completion of the tasks in the previous state, and finally the conclusion state produces a final response. They also show how this system works in action when producing a research paper, as you see in this image, and the interaction between these 4 agents of AI researcher, Google Scholar agent, academic writer agent, and PDF processing agent. As you can see, IOA also outperformed both single LLMs such as GPT-4 as well as other agentic systems such as AutoGen across general AI assistance benchmark, even in the more challenging level 2 and level 3 tasks, which demand advanced reasoning and intricate collaboration. The IOA system also outperformed both AutoGPT and OpenInterpreter in various testing categories such as math, coding, and search and report, which shows IOA's proficiency in gathering and synthesizing information as well as in collaborative problem solving. Feel free to pause the video to read these example instructions across the 4 mentioned categories that were included in the IOA open-ended benchmark. But that's not all. IOA also outperformed multi-robot collaboration, as you see in the visualization of Rokobench, which is a tabletop test of manipulation of objects that are easy to understand for LLMs but hard to collaborate. For example, the cabinet task requires 3 agents to collaborate. 2 agents open and hold the cabinet door, while the 3rd agent retrieves 2 cups from inside the cabinet and places them onto coasters that match the color of the cups. I will leave a link so you can check out other fun robot tasks, such as the famous sandwich task, the challenging sword task, and the frustrating rope task for multi-agent collaboration systems such as IOA. You might have heard of or used the mixture of expert models such as Mixtral, but have you heard of the mixture of agents? The mixture of agents or MOA method is an update to this series that explores how multiple AI agents work together and how to set up repeatable agentic workflows for more complex tasks. This framework took inspiration from the mixture of experts method in machine learning. Originally discussed in the paper, Mixture of Agents Enhances Large Language Model Capabilities, the authors propose a layered MOA architecture wherein each layer comprises multiple LLM agents. Each agent takes the outputs from agents in the previous layer as auxiliary information in generating its response. They noticed that current LLMs are restricted to their model sizes and training data, and that scaling them is super costly and computationally intensive. As I explained in my previous videos, the direction that many AI companies have taken to produce a single all-purpose model with all types of capabilities to replace the multitude of available models with unique features will soon reach a bottleneck. Instead, we can harness the collective expertise of multiple LLMs to create a more capable and robust system, whereby diverse models with particular strengths and unique data for special use cases benefit each other's responses for more complex and demanding tasks. As this architecture demonstrates, multiple agents depicted as A receive the initial prompt and generate responses independently as shown with different colors. Each response is then passed forward to the corresponding agent in the next layer for further refinement. The second layer may or may not use the same model when refining the responses. This iterative refinement process continues for several cycles until obtaining a more robust and accurate response. The most interesting part of this layered approach is the automatic selection of models for the next layer based on their performances. For example, the average win rates in the previous layer. The model selection also takes into account model diversity. They notice that the responses generated by a diverse pool of models contribute significantly more than outputs produced by the same model. These 2 criteria, model performance and diversity, are used as the basis of collaborative synthesis that can compensate for the deficiencies of a single model and improve the overall quality of responses. Something that just struck me is that we all tend to do this in our daily and work lives. Compare a single-person company that does all the chores and has to spend a lot of time learning virtually every skill, and a company that hires multiple top talents for multiple specialized positions where they collaborate on a task, sharing their feedback and understanding. This directly takes me to the collaborative aspect of this mixture of agents framework, which is composed of proposers and aggregators. Proposers are the agents that generate useful reference responses to be used in the next layers as insight or direction for the final output or modeled responses. Aggregators are agents with specialized proficiencies that receive the context and perspective from the proposer agents and synthesize the information into high-quality final responses. An MOA system can effectively have multiple proposers and multiple aggregators, depending on the task complexity and the choice of model. An exciting feature of this framework is that it doesn't require any technical knowledge, for example, for fine-tuning. All specifications happen with natural language in the prompt. The authors then evaluated a 3-layer architecture with 6 open-source models, including Llama 3 and Mixtral, and the Qwen 1.5 chat as the aggregator in the last layer, and compared it against the single LLM GPT-4. The evaluation was done based on 3 benchmarks: Alpaca Eval 2.0, which is an automatic evaluator of large language models with a very high correlation with human performance; Empty Bench, which is a series of open-ended questions that evaluate a chatbot's multi-turn conversational and instruction-following ability; and the third benchmark, Flask, or fine-grained language model evaluation based on alignment skill sets, which produces fine-grained scores for both human-based and model-based evaluation. They found that the responses produced with this mixture of agents framework outperform single LLMs such as GPT-4o responses on the Alpaca benchmark, as you see. The MOA method also outperforms GPT-4o on the Flask benchmark in other areas such as completeness, metacognition, and factuality. There are so many new advances in AI agents that I will share with you in future videos, not to make these videos super long. But one more agentic system that I wanted to explain is this super cool Adala system, which was introduced several months ago, but honestly, it's so underrated. So Adala stands for Autonomous Data Labeling Agent Framework. In their GitHub repository, they described it as Adala offers a robust framework for implementing agents specialized in data processing with an emphasis on diverse data labeling tasks. These agents are autonomous, meaning they can independently acquire one or more skills through iterative learning. This learning process is influenced by their operating environment, observations, and reflections. Users define the environment by providing a ground truth dataset. Every agent learns and applies its skills in what we refer to as a runtime, synonymous with LLM. In other words, Adala is a unified data labeling system that is entirely handled by LLMs. Given the ground truth or a set of human-verified data labels which is given to the system as the training data, the system runs agents for a specific skill, for example, sentiment analysis, question answering, and text classification, while giving the agents a defined role and how to process the data. The user can also choose a specific LLM, even the models which require API keys for access. The agentic flow then starts learning from the training data and applies its understanding to your chosen set of final data or test data. Sounds like what we've been doing with supervised machine learning on our own, but it's so cool that we can reach such a high labeling accuracy with LLMs that we can effectively trust them to do the entire process on their own. I believe one thing that they can add to this system is a chat-like interface where new instances can be given on the fly to make the experience a bit more informal. If you like this video, consider subscribing and let me know if you have a plan or idea to use an agentic AI workflow for your projects.